Taking a look at number 46 here in 9.6. They refer us back to section 9.3, exercise 44. You've got a circuit with alternating current. They give you these two equations here. You've got this 40 sine of 250t plus 30 and this 60 sine of 250t plus 60. The phasors involve the magnitude and the angle measure. So you can see here, and this is if you go back and look at that problem from 9.3, you've got a 40 and you've got a 30 being added there. That gives you that phasor. You've got a 60 and a 60 being added there, and that gives you that phasor. Okay? They're telling us to convert these to complex numbers. You've got a magnitude and an angle. Okay? So I've never worked with either of these before, but I can convert a magnitude and an angle to complex numbers. It says to add them and then write a function that gives the total voltage in the circuit. Well, you're going to get a magnitude and an angle, and so your new function is going to have a magnitude and an angle being added to this 250t, and that's going to be your final equation. So what's this going to look like? Well, I set this up here. So I've got my phasors over here. So I took a complex number with a magnitude of 40 and an angle measure of 30, and I converted that to cosine I sine form. Okay, so I've got this. That'd be 40 cosine of 30 plus, they use a j in electrical engineering instead, so j sine of 30, but same thing as plus I sine of 30. Cosine of 30 is radical 3 over 2. That's 1/2, so that simplifies to 20 radical 3 plus 20j. If we've got a magnitude of 60 and an angle measure of 60, that would be 60 cosine of 60 plus, again using j sine of 60. Cosine of 60 is 1/2. If you multiply that out, it's 30. And sine of 60 is radical 3 over 2, so you get 30 radical 3j, okay? It asks you to add these two things together, okay? You're going to be adding your real parts and your imaginary parts. So you're going to be adding that 20 radical 3 and the 30. It's going to be some kind of ugly value, so I would convert that into a decimal. Same thing with this 20j and this 30 radical 3j. So anyway, I added those together. I got approximately 60.041 as the real part and about 71.962 as the imaginary part. So again, using a j there with that. From that point, I need the magnitude and the direction of that to take it back into the original form. So I guess first to get a phasor and then to take it back into the sine function form. So magnitude, or actually I guess the absolute value is really a better term to use here, or the modulus is probably an even better term. So use the Pythagorean theorem here. The modulus ends up being about 96.731, so that's going to be the multiplier out in front of my sine function. And then I used an inverse tangent, right? Because if you plot this, what you're doing is you're going over 64 in the essentially real direction. You're going to graph this. If you've got a point here, you're going over about 64.041 in this direction, and you're going up about, going over this far, and you're going up about 71.962. Okay, and you're trying to find this angle measure right there. So I've got an opposite and an adjacent. I can use an inverse tangent to find that. So I used my inverse tangent there. It's about a 48-degree angle, depending on how you want to round it. So my phasor ends up having a modulus of about 96.731. The angle measures about 48 degrees, okay? So I just substituted that back into those two positions in that equation. Again, I don't have a lot of background as an electrical engineer, but the modulus value went here, and the angle measure is being added to that 250t, which must have some other purpose in this problem. I guess that would have to do with how often this wave is repeating. And that's all you got to do.